everybody. Welcome back to Monte Carlo methods. In the last video, we were talking about the Kolmogorov-Smirnov test, which is a way to test whether or not your simulated values from a one-dimensional continuous distribution are close enough to the target. In particular, we used it to test for uniformity from a random number generator. Now, we want more than one thing out of our random number generator. We want simulated values to appear to not only be uniform 0, 1, but to be independent. We want them to be realizations of IID uniforms. And in this video and the next, we're going to talk about tests for independence. Now, most people will tell you that there is no such thing as a test for independence in a situation like this, and they would not be entirely wrong. But what we can test for are things consistent with independence. For example, and just to make this a simple example, let's not talk about independence yet. Suppose I want to test whether or not my values are coming from a uniform 0, 1 distribution, and I don't know the Kolmogorov-Smirnov test. One thing you might do is say, the true uniform 0, 1 distribution has mean 1/2. And my simulated values have a mean pretty close to 1/2. So you could do a formal hypothesis test. A test about the mean is usually one of the very first tests you learn about in hypothesis testing in statistics. And there's error in hypothesis testing, which comes from the fact that you're never looking at all the data you can generate, just the ones you did generate. But for the sake of argument, let's assume there's no error. So you can either truly conclude that the true mean is 1/2 based on just your sample, or the true mean is not 1/2. If you conclude it's not 1/2, then you know your data did not come from a uniform 0, 1 distribution. But if you can conclude that the mean is 1/2, you still don't know that you came from a uniform 0, 1 distribution, but you have evidence that is in line with it coming from a uniform 0, 1 distribution. So I wouldn't conclude uniform 0, 1, but I've got another piece of evidence towards that end. This is the idea. We're going to be testing for things consistent with independence, and all the tests we talk about, I would not run or trust any one of them alone, not even close. But if you run them as like a big suite of tests and you pass all of them or most of them, then I would feel good about saying that my simulated values are independent or realizations of something that are independent. By the way, you may have in the back of your head some recollection of, isn't there a chi-squared test for independence? There is, but that is a different scenario. That is for testing the independence of two or more categorical variables. Not only are we not generally talking about categorical variables here, and definitely not with the random number generator, we're not talking about multiple random variables, but multiple copies from one distribution. So that chi-squared test that you might be thinking about just doesn't apply here. I said we'd be testing for independence in 2 videos, and I'm only going to do one test today, and I'm going to do it in some detail. In the next video, I'm just going to sort of rattle off a bunch of other tests that are similar and not go into as much detail. So this one will be kind of the slow walk, and in the next video, we'll knock a lot of tests out of the way. A lot of these tests for independence are runs tests. What does that mean? Our very first test is a runs up or down test for independence. The basic idea is if you were to simulate values from your random number generator or another univariate continuous distribution, you get a first value and your second value is, say, larger, and your third value, it might also be larger than that. Your fourth value, even larger than that. Your fifth, if you see a long run of numbers going up or a long run of numbers coming down, then you may start to think that they're not independent, that you have some correlation here. So that is the basic idea for a runs up and down test. Before getting into our first runs test, I have a quick interesting claim for you. Suppose that capital X1 and capital X2 are IID from any continuous distribution. I claim that the probability that X1 is less than X2 is 1/2. And because these are continuous, I can replace this strict inequality with less than or equal to, and you should still get 1/2. I'm going to prove this in 2 ways because I think both approaches illustrate something that you're going to find useful, and the proofs are pretty short. So my first proof, I'm going to take the math stat approach. That's what I would call it. And I'm going to assume in both cases, in both proofs, that there is a PDF for this distribution. For most continuous distributions that I think you're going to be interested in, this is going to be true. If it's not, Well, it's a simplifying assumption for this proof. So let's get into the proof. The joint PDF for capital X1 and capital X2, I'm going to call this little f of little x1 and little x2. And because they are IID, this is just a product of the individual PDFs, which each involve the same function, one with little x plugged in and the other with little x2 plugged in. To compute the probability that capital X1 is less than capital X2, one way to do this is to integrate the joint PDF over the appropriate region. So I'm going to integrate dx1 and then dx2. You can do this the other way around. But the way I have it, I am going to come up with the appropriate limits of integration now. So the outer integral, the way I've written it, is with respect to x2. I'm going to run over the whole space, which in general is minus infinity to infinity. For a particular PDF, like the uniform 0, 1, you might only be going from 0 to 1, but it never hurts to go from minus infinity to infinity, because in a case like that, your PDF is going to be 0 outside of the region 0 to 1. So if I integrate from minus infinity to infinity, I'm just picking up a whole bunch of zeros. I'm going to let my outer integral, my dx2, my x2, go from minus infinity to infinity. And then for each x2, I'm going to restrict x1 to go everywhere from minus infinity to x2 so that we are looking at the space where x1 is less than x2. Again, because these are IID, I get to break up this joint PDF into fx1 and f of x2. And now I'm going to pull the x2 stuff out of the inner integral. And my inner integral becomes the integral from minus infinity to x2 of the PDF at little x1 dx1. But that's exactly the CDF at little x2. So we end up with the integral from minus infinity to infinity of little f of x2 times capital F of x2 dx2. The CDF you get by integrating the PDF, and you can go backwards by taking a derivative. This integral is a simple U substitution, and this trick, if you haven't seen this before, is something really useful, and I'm going to use it several times in just today's video alone. I'm going to let U be capital F of x2. If I take the derivative to get the differential, then du is lowercase f of little x2, d little x2. So this integral is a u du. If you make a change of variables like this, you need to change the limits of integration. But if you don't want to bother, then go through the integral to the end. Make sure you plug the capital F of x2 back in before using the limits of integration, minus infinity to infinity. But this limit change is easy enough. If x2 is minus infinity, then u is capital F of minus infinity. Yes, it's a limit, but the CDF at minus infinity is always 0. And when little x2 is positive infinity, u is the CDF at positive infinity, which is always 1. So my u goes from 0 to 1 here. And we get the integral from 0 to 1 of u du, which is, of course, u squared over 2 evaluated from 0 to 1. And you get 1/2, which is what we wanted. So now the Markov approach. I again want to try to compute the probability that capital X1 is less than capital X2. The Markov approach would be to say, I've got too many random variables here, so I'm going to condition on one of them so I can fix it. This is equal to the integral from minus infinity to infinity of the probability capital X1 is less than capital X2, given that capital X2, just as an example, I could have picked X1, but given that capital X2 is equal to some little x times the quote unquote probability that capital X2 is equal to little x. Now that probability is always 0 for continuous random variables like this, but that means that we should use the PDF as opposed to a probability. So I multiply by the PDF, which represents the probability that capital X is equal to this observed little x, and then I integrate and run over all of those x's. If it bothers you here to see a continuous random variable set equal to a specific value, note that this is after the conditional given line. If I could measure someone's height, say in inches, with an infinite accuracy ruler, and I randomly select a person from campus and measure them, the probability that I'm going to find someone who's exactly 67.128331507 inches is infinitesimally small. And in fact, the probability I'm going to find someone at any exact height is 0. But once I observe that person, once I choose that person and they're in front of me and I have my infinite accuracy ruler, I measure them with infinite accuracy and I can say, your height is exactly this. So All of that is to say that if you have a continuous random variable equaling a number after a given sign, it's been observed, that's okay. If something like this was on the left side, the probability would end up being 0. So to continue, the first thing I'm going to do is plug in this little x for capital X2 over here. We end up with this. And now I am going to drop the stuff after the conditional line. Why can I do that? Number one, I've used the information, but that's not enough. The other thing is, at this point, I have one random variable on the left side of the conditional line, and that's capital X1, and another random variable on the right side, capital X2, and those are independent. So even though there's no capital X2 explicitly on this left side of the conditional line, it could be in general that the distribution of capital X1 depends on the value of capital X2. It acts differently depending on where capital X2 is, but that's not the case here because they're independent. So I'm going to drop this conditional information. Once I do, we end up with this, and I don't really need to write this next line, but I'll do it just once. I'm going to skip it the rest of the time today. Because things are continuous, I can replace this strict inequality probability with less than or equal to. And now what you see is the CDF for X1 or X2, they're IID, but the CDF, capital F, evaluated at little x, times the PDF at little x dx. And to do this, it's another U substitution. It's the exact same U substitution. Let U be capital F of x, then du is little f of x dx, and go, and you'll get 1/2 because this is the exact integral we did in the mass stat approach. Now that we have that very exciting claim out of the way, let's get back to the idea of a runs up or down test for independence. What I'm showing you here are 21 values I generated with a random number generator in R. I have written the values so that you can read them on a slide, but they should be read from left to right across rows. So this is the first, second, third, fourth, fifth, sixth values, etc. Order is important if you're trying to look for like correlations and relationships between consecutive values and things like that. So order is important when you're doing this test. The first number is 0.44 something. The second number is 0.07 something. So the first number is starting a run going down. The third number is 0.33, so I'm going back up again. So this run going down ends right here. And what you're seeing is a run down of length 1. Now in today's test, I don't care about the length of the runs at all. I will care about them in the next video. But for the record, it is a run down of length 1. So the run has ended and we're starting over. You should start over with this value. Okay, starting here, between here and here, I'm going up. And then between here and here, I'm going up again. So I have started a run up, and it appears that that ends right here because between here and here, I go down. So I have a run up of length 2, but again, I don't care about the length today. Just thought I'd throw that in there. If you continue and go through this slide, I have n equals 21 observations, and I have 5 runs up and 6 runs down for a total of 11 runs. For this test today, I don't care whether they're going up or down. I care about the total number of up-down runs, in this case, 11. Question is that good for a sample of size 21? Do you expect to see somewhere close to 11 runs up or down if these data are assumed to be independent? Let's get out of this sample and talk more generally. Suppose that capital X1 through capital Xn is a random sample from any continuous distribution with a PDF lowercase f and a CDF capital F. I'm going to define capital R sub n to be the number of up-down runs in this sample of size n. And the question is, what do we expect R sub n to be, i.e., what is the expected value of R sub n? So how are we going to count these runs? How are we going to compute R sub n? For I equals 1, 2, up through n, I want you to consider the indicator random variable, capital I sub I, that takes on the value 1 if capital X sub I is starting a run, up or down, it doesn't matter, and 0 otherwise. Now, the total number of runs in the sample of size n is going to be to sum these indicators as I goes from 1 to n, because you're going to get a 1 every time you start a run and a 0 when you're not starting a run, maybe in the middle of a run. And so if you add up these 1s and 0s, that counts the total number of runs. And if you want the expected value of R sub n, you can put this whole sum into the expected value. It's a nice linear operator. You can pull the sum out. So it really comes down to, can we compute the expected value for these indicators? All right, let's look at the first indicator. Note that capital X1 The first value in your sample is always starting a run, either up or down. So the first indicator, capital I sub 1, is always 1. You can think of this as a constant, or you can think of it as a boring random variable that takes the value 1 with probability 1. One that's, I think, a little bit less obvious is that capital Xn never starts a run. And just if you're not convinced, just think about this a little bit. Like if you're at the end of looking at your values and maybe you're 2 away from the end. So if you're going down, but then on the very last value, you're going up, it's really that second to last value that is starting that run up, if that makes sense. And you would actually need an n plus first value to see whether or not xn is starting a run. So it's not starting a run. And that means that the indicator I sub n is always 0, which you can think of as a constant or a really boring random variable. So given that we've locked a couple of these indicators in, I can write the expected value of Rn as 1 plus the sum as I goes from 2 to n minus 1 of the expected value of I sub I. So let's find this expected value. For any I from 2, 3 up to n minus 1, the expected value of I sub I, it's a discrete random variable. It takes on the values 0 and 1, so we get 0 times the probability the indicator is 0 plus 1 times the probability the indicator is 1. This is just the probability the indicator is 1. The indicator is 1 if and only if the x sub I is starting a run. So this is an equivalent event. We get the probability that capital Xi is starting a run. If it's starting a run, it's either up or down and can't be both. Those are disjoint events. So I can break this into a sum of the probability that capital X sub I is starting a run up plus the probability it's starting a run down. I claim these are equal. So this would be then 2 times one of these. And if you believe this, great. If you don't, it's not something I would go off and try to maybe prove as much as I would follow the steps that we're about to do to compute this probability and just make a subtle alteration to compute this probability and just see that you get the same thing. I think that's the easiest way to prove it to yourself if you don't believe it. I'm just going to claim it, though, in the interest of time and compute only one of these probabilities. Okay, so what is the probability that x sub I starts a run up? To figure this out, I'm going to just actually look at an example. I'm going to throw down some slots or positions here labeled I minus 1, I, and I plus 1. If x sub I is supposed to be starting a run up, that means that the number I put in this position has to be larger than the number I put in this position. And that's not all, because if it's starting the run, then x sub I can't be in the middle of a run up, which means it has to be the first place things turn around. So I need to have a number here that gets then smaller here and then larger here. I put some integers in just to have a really clear slide, but you don't want to be doing any sort of runs analysis with discrete random variables because you have ties then. What happens if you see 777? This is not what we're talking about today. So I put integers only just to, illustrate up and down. Okay, so what you can see here is the probability that xi starts a run up means that x sub I has to be smaller than x sub I minus 1, and x sub I has to be smaller than x sub I plus 1. And in probability, if you're not talking about events and sets where it would be an intersection, for random variables and becomes a comma, this is just notation for the line above. So how do we compute this? I'm going to take that Markov approach, and because I look at this and I see way too many random variables. So if I can condition on the value of 1 or 2 of these and get it to be a fixed number, things would be a lot easier. Because I have a capital X sub I in both of these inequalities, that's what I want to condition on, because I really want to separate things out and not have 2 random variables together in an inequality. I can rewrite this probability as the integral from minus infinity to infinity of the probability that you see right here, given that x sub I equals a value x, multiplied by the PDF for x, and then dx. We're going to run over all of these x's. 2 things happen next. I'm going to plug in this little x for capital X sub I, and I'm also going to drop this conditional stuff because I have used up the information. Number 1, I don't need it anymore. And number 2, capital X sub I minus 1 and capital X sub I plus 1 are independent of capital X sub I. So they're not going to need this information, and we're not going to need it to compute probabilities involving capital X sub I minus 1 and capital X sub I plus 1. So I'm dropping this. Once I drop this, I'm left with a joint probability here that can factor into two probabilities by independence of these two random variables. So where are we? The probability that x of I starts a run up is written like this now. And both of these are, if they were less than or equal to probabilities, they'd be CDFs. They are the complements. So both of these are 1 minus the CDF capital F at x. So we end up with this. And now I can do a U substitution. I'm going to let U be 1 minus capital F of x. It's fine if you want to let it be just capital F of x. Things will be slightly different, but in the end, we'll be in the same place. And this means that du is the derivative of this, which is 0 minus. So we get negative little f of x dx. And if you want to change the limits of integration, rather than going through to the end and putting the x's back and leaving the original limits, note that u here is going as x goes from minus infinity to infinity. The CDF is going from 0 to 1, and 1 minus the CDF is then going from 1 to 0. So we get the negative of the integral from 1 to 0 of u squared du, which is the positive of the integral where we flip back the limits of integration. We get the positive integral from 0 to 1 of u squared du. And if you finish that, it's 1/3. So let's pull it all together to get back to the expected value of the number of runs. For I equals 2, 3, up through n minus 1, we have that the expected value of the ith indicator is 2 times the probability that x of I starts a run up. We just computed that. That was 1/3. So the expected value of I sub I is 2/3. This means that the expected number of runs in a sample of length n, up-down runs, is 1 plus the sum as I goes from 2 to n minus 1 of these expected values that are all 2/3. There are n minus 2 terms in the sum. We get n minus 2 times 2/3. And when you add the 1, you end up with 2n minus 1 over 3. By the way, this is going to be useful in a moment. Note that I sub I, this indicator random variable, is a Bernoulli random variable. The p for the Bernoulli, the probability it's equal to 1, is the same thing as the expected value for an indicator. And so p here is 2/3. I'm going to need this in a few minutes. But we know the expected number of up-down runs in a sample of length n. So what can we do with this? We're going to try to do essentially a hypothesis test while I try to avoid most of that language. And knowing the expected value is not quite enough. We want to know how variable it is. And really, we need to know the distribution of R sub n. So we can say a little bit more. We can say, okay, we didn't meet that expected value, but how much does it vary? How does it act? So what is the distribution of R sub n? You may look at this and think this is a sum of Bernoulli random variables and therefore is binomial. But note that that's only true if the Bernoullis are IID. They are one of those I's. They are identically distributed because each of these is Bernoulli with p equals 2/3. But we don't know that they're independent. I don't know what you think about this at that point, but I will convince you eventually they are definitely dependent, or at least some of them are. So a sum of dependent Bernoullis, that's really difficult to work with. The runs up and down tests are usually done for large samples and approximately using the central limit theorem because I have a sum here of random variables. And depending on how deep you are into statistics, the first central limit theorem you learn about is for IID random variables, and these are not independent, but there are in fact versions of the central limit theorem that apply in certain cases with dependence. So that's what we're going to use here because I claim we're going to see dependence between some of these indicators. So according to the central limit theorem that may involve dependent random variables, this sum is going to act roughly normal. And if you add a constant to a normal, it still has a normal distribution. So overall, this quantity is going to roughly act like a normal random variable with mean 2n minus 1 over 3 and some variance. For the moment, I'm going to write Rn, squiggly line, has the distribution, and put approx for approximate across here. It's approximately normal with mean 2n minus 1 over 3 and some variance. If you've had math stat or more advanced courses, you'll know that this is actually an asymptotically normal result involving convergence and distribution. That's totally unimportant here for where we're going with this. Basically, I just need to know that it's acting approximately like a normal distribution. So that's how I'm going to write it in this course, where I'm not assuming all of that background. Kind of am. It's kind of sneaking in all over the place, isn't it? But hopefully some of you are hanging in there. So What is the variance? The variance is actually 16n minus 29 over 90. If you want to see that, stick around to the end of this video after my little outro animation, and I'll show you how to compute that variance. But it is tedious and long, and I didn't want to lose people in the middle of the video, so it's separate, so you don't have to be fast forwarding and trying to find where I pick up the video again. For the moment, I want to assume we know that this variance is 16n minus 29 over 90. Once we have that, the bottom line is that for large n, usually considered in this case n greater than 30 or 40, our n is approximately normally distributed with mean 2n minus 1 over 3 and variance 16n minus 29 over 90. This means that if you define a new random variable, capital Zn, to be Rn minus its mean divided by its standard deviation, you'll get something that is approximately normal 0, 1. Now, for a normal 0, 1 random variable, if you want to get it between two numbers with, say, probability 0.95, I'm thinking confidence interval coming, you can get those critical values for a standard normal distribution. They're typically taken to be, for capturing area 0.95, the numbers negative 1.96 and positive 1.96. You can choose to pick them asymmetrically. If you want to know more about confidence intervals and choices for things like this, take my math stack course. But the fact that Zn is approximately normal means that the probability it's between negative 1.96 and positive 1.96 is approximately 0.95. And if I plug in what Zn is, it was Rn minus stuff divided by the square root of stuff, I get this as approximately 0.95. So now I want to kind of solve down in this system of inequalities for Rn in the middle. I want to isolate Rn in the middle. And we get two endpoints, which make up an approximate large sample 95% confidence interval for what Rn should be. It ends up being 2n minus 1 over 3 plus or minus 1.96 times the square root of 16n minus 29 over 90. If you look this up in a book somewhere, you might see a 2 used for 1.96 because everything's approximate anyway. So why not? On the other hand, everything's approximate anyway, so why make it worse? I don't know. 1.96 is not exact as well, but it's all wildly approximate. But in the end, here's what this is saying. If we simulate a large sample of size n, so n is large, from any continuous distribution, univariate, including our random number generator, then we expect the number of up or down runs to fall in this interval approximately 95% of the time. What does of the time mean? For your one simulation of size, say 100,000, it will be in there or not. There's no of the time. But what it means is if you were to repeat it and get a new sample of size 100,000 and a new one and a new one, approximately 95% of those large samples, if you computed up-down runs, the runs will fall between these values. So if I were to simulate 100,000 values and count my number of up-down runs, hopefully that number is in this interval. If not, all is not lost. In fact, it shouldn't always be in this interval. If it's easy for you to do, simulate another 100,000 values and check again and again and again. And if you went through many simulations, each with 100,000 values, then 95% of those approximately should have the number of up-down runs counted falling in this interval. So this whole test was predicated on these things being independent. It is a result consistent with what you should get if you have independence in your sampled values. But it is hardly a test for independence on its own. Make sure you look at more tests for independence like in the next video. So this is all I really needed to say today. If you stick around after my little outro, if you care about computing that variance, 16n minus 29 over 90, let's do it. Stick around. Otherwise, I hope to see you in the next one. Awesome, you're still here. You're definitely my kind of people. You want to know how to compute this variance. In order to do this, you are going to need to know about covariance. Otherwise, none of this is going to make sense. Not only are you going to need to know the definition of covariance, but operations you can do with covariance, like pulling sums in and out. If you don't, I would leave now because this isn't going to make any sense. And I wouldn't worry about it really for the purpose of Monte Carlo methods. But if you want to follow the variance and you don't know about covariance, you might stop this video at this point and check out this video I have about covariance and properties of covariance, and then come back. Okay, so you're still here, so let's go ahead and compute the variance of Rn. The variance of Rn is the variance of 1 plus this sum of indicators. This random variable in here, the variability is all right in here, and if that can be moving around on a number line if you actually observe values, and if you add 1, it's just moving around up here. That's not changing how variable it is, so we can drop a constant, an additive constant in variance. We want to compute the variance of this. The next thing you might want to do is just pull this sum out, but that's not true in general. That's not something you can do for variance because the variance involves squares, and squares don't work like that with sums. You might have done it in the past. If things are independent, you can pull that sum out of the variance, but I claim things are not independent here, or at least we're not sure yet, so I'm not going to pull this sum out. What am I going to do? Note that the covariance between a random variable x and itself is the same thing as the variance. So I'm going to rewrite this variance of this sum as the covariance of the sum with itself. The second sum, I changed the index from little I to little j. It's the same thing though. I just wanted to avoid confusion with these two sums. It's a property of covariance that you could pull sums right out. So I'll pull both of these out and I have a double sum of a bunch of covariances. And we need to compute these terms. I'm just going to compute two of them, really one, because one of them we're getting almost for free. And then say, etc., because this is long and tedious. What is the covariance of I sub I times I sub j? As you know, since you're still here and you promised that you either know covariance or you went and looked at that video, this is the expected value of the product of indicators minus the product of the expected values. Each of these expected values we computed in this video, they are 2/3. So we get the expected value of the product of the indicators minus 4/9. Now, to compute the expected value, the product of indicators, there are a lot of cases to consider. And as I said, I'm just going to do a couple. The first case I'm going to consider is probably the easiest case to consider. I'm going to assume that I is anywhere from 2 to n-1 and j equals I. I'm actually not going to go for this expectation, but directly for the variance in this case, it's not so bad at all. So suppose you want the covariance between the indicator I sub I and I sub j. If j is I, this is the covariance of I sub I and I sub I, but the covariance of something with itself is just a variance. So this is the variance of I sub I. But we said that the indicator is a Bernoulli random variable with p equals 2/3, and the variance of a Bernoulli is p times 1 minus p. So we get 2/3 times 1 minus 2/3, or 2/9. So that case was relatively easy. I'm going to look at one more case, and then I'm going to tell you what the rest are. As the next case, I'm going to let I go from 2 up to n-2 and consider when j is I plus 1. So you'll notice I cut off I didn't go all the way up to n-1 because I don't want to go off the end when I'm looking at j equals I plus 1. The expected value of the product of these indicators, this product, these are both 1 and 0. So the product is 1 or 0. This is 1 times the probability the product is 1 plus 0 times the probability it's 0. So we just end up with the probability that this product of indicators is 1. And the product of indicators here is 1 if and only if capital X sub I is starting a run and capital X plus I is starting a run. So how do we compute this probability? This can be broken up into a bunch of cases, 4 cases, although don't get ahead of me, but I'm going to write this as the probability that X sub I starts a run up and X sub I plus 1 starts a run up. Don't get ahead of me. And then the probability that X sub I starts a run up and X sub I plus 1 starts a run down, etc. 4 cases, up, 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 down, down, up, and down, down. If you looked at this first case and said, can X sub I start a run up and X I plus 1 start a run up? The answer is no. To start our new run up, you have to have been coming down. So you can't start a run up and then start a run up again with 2 consecutive values. Similarly, we can't have X sub I starting a run down and X sub I plus 1 starting a run down. So this probability is 0 and this probability is 0. And to get through this video is getting really long already, I claim that these 2 probabilities are the same. If you don't believe that, then you can take what I do to compute one of these and alter it to compute the other one, and you'll see that they're the same. Let's look at just this one right here. Let's compute the probability that capital Xi starts a run up and capital X sub I plus 1 starts a run down. And just like I did before in this video, I want to sort of envision a scenario where this might happen. So I'm going to make some positions here for the values for Xi minus 1, Xi plus 1, and Xi plus 2. If I want Xi to be starting a run up, then I need to be coming down before I hit X sub I because I want it to start a run up. So I need a number here that maybe then goes down to a number here. And then I want to go up, so a larger number here. And then I want to go down again, so a smaller number here. As I already mentioned in this video, you should not be doing this with integers. To talk about runs up and down, it's a whole different ugly mess because there are ties. But I used integers just to have simple examples of numbers going up and down. But you can see from this that this probability that we care about, we can write as the probability that X sub I minus 1 is greater than X sub I, and X sub I is less than X sub I plus 1, and X sub I plus 1 is greater than X sub I plus 2. To compute this, I'm going to use our conditioning trick from today. And because there's so many variables here, I think I'm going to need to condition on not just one, but two. And the two I'm going to choose are the two that appear in most of these positions because I really want to separate out random things and non-random things. So I'm going to choose the X sub I and the X sub I plus 1 because at least one of those appears in all three of these inequalities. If I condition on both of these, I need to do a double integral. I'm going over the whole space from minus infinity to infinity in general. I'm going to rewrite this and then say given X sub I is little x and X sub I plus 1 is little y, and then multiply by the PDF for X sub I at x and the PDF for X sub I plus 1 at y, and then dx dy, or if you choose dy dx. I'm going to plug this little x and little y in over here every time I see a capital X sub I and capital X sub I plus 1 respectively. And then I do get to drop this information because A, it has been used, and B, after it has been used, the random variables that are left on the left side of the conditional line are independent of what's going on over here, so I can completely drop this. I do have something kind of weird looking going on right in here. In this probability statement, I have little x is less than little y, and these are not random variables. How do I deal with something like this? I want to look at, leave this problem for just a second and look at a simpler example. Suppose you want to compute the probability that a random variable x is less than 3 and 1 is less than 5. 1 is always less than 5, so the probability that you're looking at here is really just the probability that x is less than 3. Whereas if you want to compute the probability that x is less than 3 and 1 is greater than 5, that is never happening no matter what happens with your random variable x, and this probability is 0. This is what I want to do from the using on that previous line, from the last line on the previous slide. Basically, probability is going to be 0 for certain values of little x and little y, and for other values, that little x less than little y is just going to be irrelevant. I can sort of drop it like I did here. Well, little x and little y are being run over in the limits of integration here, so I'm just going to end up changing the limits of integration. Here's what I had, and if the way I have it, my y variable is on the outside, so I'm going to let those go from minus infinity to infinity, but according to this little x less than y, I'm going to make sure my x is always less than y, so my dx goes from minus infinity up to y. If you're wondering what happened to the other part of this integral, for that part, the integrand is 0, so it's gone. I'm going to use independence again right here to break this up into a product of probabilities. The probability that capital X sub I plus 2 is less than y, because it's continuous, it might as well be less than or equal to y, and this is just the CDF, capital F of y. This other one is a tail probability, a greater than probability, so this is going to be 1 minus a CDF. We're going to end up with something that looks like this. My inner integral is with respect to x, so I'm going to pull all the y stuff out and be left with this. And now it's a u substitution problem. You can let u be 1 minus capital F of x. You can let it be just capital F of x. I'm going to choose that one this time. Then du is little f of x dx to change the limits of integration. When x is negative infinity, then u is f of negative infinity, which is 0. And when x is y, then u is capital F of y, which is capital F of y. So I get for this inner integral, the integral from 0 to capital F of y of 1 minus u du. And if you do that, plug stuff in, you get capital F of y minus 1/2 capital F squared of y. To finish this integral out, you need to replace this entire parenthetical integral here with this quantity, and then multiply this CDF and PDF across, and you'll have an integral minus an integral, and each one of those will involve a similar u substitution and blah, 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 blah. When you finish, you should end up with 5/24. So if you actually tried to work that out and you're having trouble with it, let me know in the comments below and I'll say more about that. But I think I'm going to leave that there. Well, let's finish this up. The probability that xi starts a run and xi plus 1 starts a run, we broke down in 4 ways: up, up, down, up, down. We noted that 2 of them were 0, and the other 2, one of them we just computed, are 5/4. When you add these all together, you get 5/12. But we were trying to compute a covariance. And for I equals 2 through n minus 2, we were trying to compute the covariance between the indicator I sub I and the indicator I sub I plus 1. We noted that this was the expected value of the product of the indicators minus 4/9. The expected value of the product, we noted, was the probability that x sub I starts a run and x sub I plus 1 starts a run, and we just computed that. That is 5/12. So when you take 5/12 minus the 4/9, you end up with negative 1/36. The covariance between these two indicators is not 0. This tells us that the indicators are dependent. If you have independent random variables, the covariance is always 0. The reverse is not necessarily true. So if I got a covariance of 0, I still am not sure whether the random variables are independent or dependent. But the covariance being non-zero shows us that these random variables have some dependence. So it's a good thing we didn't try to pull that sum out of the variance of the sum of the indicators. So we have the covariance between I sub I and I sub I. We have the covariance between I sub I and I sub I plus 1. I'm going to organize these and other covariances in a matrix. So the rows of this matrix are me going through the indices for the different indicators. So lowercase I is going from 2 to n minus 1. And here are my j variables. So what this is saying right here is the covariance between the indicator I sub 2 and I sub 2 is the variance of the indicator, and that's 2/9. That's the same for the indicator I sub 3, I sub 4. I have 2/9 running all the way down the diagonal here. What we just saw is that the covariance between, say, the indicator I sub 1 and I sub 2 is negative 136. So that's right here. Covariance is symmetric, so you should get negative 136 if you computed the covariance between the indicator I sub 2 and I sub 1. And in fact, all of my first off the diagonal entries are negative 136. If you went on and did more computation, you would see that the covariance between an indicator I sub I and I sub I plus 2 is positive 1/180. And if you go further apart in the indices, that the covariances are 0. I have one more slide for you. We're almost done. The variance of the number of runs to be expected in a sample of size n when simulating IID things is the sum as I goes from 1 to n minus 1. The sum as j goes from 1 to n minus 1 of the covariance between I sub I and I sub j. I organize these all into a matrix. There's a lot of repeated values. What we had was 2/9 appearing all the way down the diagonal. And this was an n by 2 by n by 2 matrix. So I have 2/9 times n minus 2 diagonal terms. Plus, I have negative 1/3 appearing just off the diagonal on both sides. I have n minus 3 things just off this diagonal on each side. So I get negative 1/36 times 2 times n minus 3 off diagonal terms. And finally, I've got 1/180 appearing on the next diagonal, which has n minus 4 terms on both sides. So I get 1/180 times 2 times n minus 4, and everything else was 0. When you add all these up, you get 16n minus 29/90 as claimed. You are a trooper. I really hope I can say that I will see you in the next one.